to two particular reactions in last week's prep. One was the substitution of cyclohexane. The other was the addition across cyclohexene. So with cyclohexane, right, only under the presence of ultraviolet light, didn't really work. It's a pretty dull day last week. And so it meant that we still saw those immiscible layers. Yeah? What we were expecting was this to be partially soluble. See that it appeared a little bit cloudy with the addition of the light. Yeah? Cloudy day, not much I don't know how much ultraviolet light actually comes out of an incandescent globe, but a little bit would. So we would have expected it to appear a little bit cloudy. Now the bromine was already, I think it might have even been hydrogen bromide as opposed to bromine because it was already colourless. Normally bromine's got a bit of colour in it. Anyway, so the point I wanted to make today was less to do with the bracket, more about the identification of chiral centres. Bromocyclohexane does not have a chiral centre. So if we consider it, right, if I look here, I'll use my cursor. I've got three different things, or I've got one hydrogen, one bromine, and then we've got to think about when I've got a ring, I need to consider whether each direction of the ring constitute a different sequence. So if I go this way around the ring compared to this way around the ring, I end up with the same. So it's not four different substituents, therefore it's not chiral. It's an achiral centre. However, if I add bromine across this double bond, end up with 1,2-dibromocyclohexane, then I do in fact have two chiral centres. Yes, I have symmetry through this bond here, but the direction of which gives me two different ways around the ring. Because if I go this way around the ring, I have a bromine there. I don't have a bromine on here, so I can distinguish one way around from the other. So for argument's sake, in this ring, we have two chiral centres. I could then look at them in this sort of projection, showing that I can either have it where one bromine faces towards us, one behind, or I can have two face forwards. I could have two facing backwards, but that would actually be this same molecule flipped over. Does that make sense? Can you visualize that on the digital whiteboard? Yeah? I could take this and flip it over. So these are different. They are enantiomers of 1,2-dibromocyclohexane. So I wanted to make that clear. So I'd like to encourage you to download an app, right, that you can have a little bit of a play with. Yeah, right? It's called Chirality. Some of you may have come across it already. Looks something like this. Yeah, that's the symbol, right? And it's called Chirality 2. So I encourage you to download that. And there is a whole heap of different things. Recognition of functional groups within a different compound, right? Including primary, secondary, tertiary alcohols even in there, right? You can change the level of difficulty. There are some functional groups that we don't look at, such as ethers. One thing about the app I want to actually correct is that it calls OH alcohol. Whereas we know that alcohol is the homologous series, OH is the hydroxyl functional group. Yeah? So just keep that in mind when you're playing that app. There's another app I would like you to consider. I think the symbol's just changed. Looks something like that. It's got a little molecule on the front. It's got a white background, a little oxygen there. And this is called Chemical Detectives. Now, Chemical Detectives isn't useful now, but when we go into spectroscopy, incredibly useful. Chemical Detectives is produced by the CEA, which are the same people that produced your textbook. There are over 300 molecules within there, right, with spectroscopic data, and coming up towards the end, next month, they're bringing out another update that is specifically for VCE related molecules. I'm telling you it's excellent, and that wasn't from me. I had nothing to do with the app, but it is very, very good. 100% 5-star reviews. Okay, so download those two things. Chirality is a bit of fun. Chemical detectives, really good. 300 multiple choice questions relating to spectroscopy, which is our next topic, after volumetric analysis. Yeah. Okay, to finish off with chemical synthesis, two more things we need to talk about. One is atom economy, two is yield. So let's start by talking about atom economy. What does the word economy mean? Money, trade, yeah. Economics is actually the study of scarcity. So it's not necessarily always to do with money, although there's often a relationship between money and scarcity. Things that are scarce are generally more valuable, right? And what's an atom? A thing, helpful. What do we know an atom to be? Let's go back to year 8 science. What's an atom? Building blocks of the universe, fantastic. It's the smallest unit of matter before, right? Because I know you're going to talk to me about subshells and quarks and blah, 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 right? It's the smallest units of matter without changing the chemical properties, right? Because we know we can split an atom into smaller components, but if we do that, we change the chemical properties of the substance, yeah? Change it. Anyway, so atom economy, when we put those two together, has something to do with scarcity, something to do with the economics, right? The efficiency, if we want to think of it another way, of how atoms are rearranged in a chemical reaction. So what it is, it's a measure of the proportion of the reactant atoms, right, that end up in our desired product. So if we're making an ester, what's our byproduct of an esterification reaction? Water. We don't want the water, yeah? So water present decreases our atom economy, right? What happens if I've only got one product? Stanford. Good. How'd you go?
I got 9 out of 10.
Fantastic, right? If I only have one product, what's my atom economy? No. Has to be 100%, right? Because all the atoms in my reactants are completely used up into my product. So it's 100%, right? And so when we're designing synthesis or designing molecules, one of our considerations is, how many byproducts do I have? Can I make this economically more viable from a synthetic synthesis point of view? So coming on with that similar example to the one I talked about from last week's prac, if I take just ethene, add bromine across the double bond, 1,2-dibromoethane, the addition of bromine, only one product, the atom economy would be 100%. Okay. Now let's look at an example whereby it's not 100%. So let's look at the substitution. Substitution of bromine across ethane. Now, we don't just count the atoms. Yeah? Yes, it's a measure of how efficiently the atoms are used up, but we're looking more to the molar mass of the atoms. So, atom economy is equal to the molar mass of the desired product divided by the total molar masses of the reactants. Yeah? So, I'll say that again. Atom economy is the molar mass of the desired product divided by the total mass, molar mass, of the reactants. So if we look at ethane, 12 plus 12, 24, add 6, molar mass 30. Bromine, 2 lots of 79.9 gives us 159.8. Add the two together, 189.8, right, is my total molar mass of my reactants. My desired product, bromoethane, 29, because it's one less hydrogen. Add the bromine, gives me 29 plus 79.9. What's that off the top of my head? 108.9. Yeah? Is that right? 108.8. No, 108.9. That was right. Divided by 189.8 times 100 makes that reaction 57, has an atom economy of 57%. Right? So HBr is a byproduct from a mass point of view, not very efficient. Yeah. Okay? Does that make sense? Yeah? Cool. All right. Now let's talk about yield. We've looked at yield from an equilibrium point of view. Let's do a quick recap. How do we increase the yield of an equilibrium system? Right, we want to have a net forward reaction. Right, so if I've got an exothermic reaction, how do I increase the yield? Cooler. Yeah. Right, exothermic reactions favoured in cooler temperatures. So I could cool that. What else might we do? If I have one product and two reactants, what would I do in an equilibrium system? Increase the pressure. Right. Fewer products, fewer favours, right? The one with fewer particles. I would also add more reactant, drives the reaction forward. So yield is a measure of how much of the desired product is obtained in a chemical reaction. Yeah, I've seen this before. Again, I'm going to look at it from a percentage point of view. So percentage yield is the actual yield, so the mass, could be volume, but mass, right, or amount of mole. Either are going to be like related quantities. So yield divided by the theoretical yield, that's our stoichiometric proportions, multiply it by 100%.
Do you then work out, can you work out the yield error?
The yield error, yeah, I guess you could do the percentage of yield error based off the difference between the two. Yeah, not something you really have to worry about. Don't have to worry about uncertainties in year 12 BCE. So here's an example. 20 mils of 1 molar HCl added to 2 grams of calcium carbonate. The amount of carbon dioxide measured in the experiment was 0.2 grams. What is the percentage yield of this reaction? Right, so the first thing we need to do is determine what the theoretical yield of that reaction would be. And what we want to do, so we set up balanced chemical equation. Hydrochloric acid plus calcium carbonate gives us calcium chloride plus carbon dioxide plus water. Yeah? Put in my known values. Hydrochloric acid, number of mole equals concentration times volume. I've got 1 molar times 0.02 litres. 0.02 mole. Cool, makes sense. Calcium carbonate, I've got 2 grams. It's not a solution, so N equals CV doesn't make sense. I'm going to use N equals M1N. 2 divided by the molar mass, which is 40.1 plus 12 plus 3 lots of 16 is 100.1. I end up with 0.02 mole. So I happen to have 0.02 mole of both HCl and 0.02 mole of calcium carbonate. However, one of them is in excess, right? As I'm balancing this chemical equation, I have a 2 here. So I need twice as much HCl. Ned. Yeah. So I need twice as much. So I can look at that and just determine HCl must be limiting because I need twice as much of that as my calcium carbonate. So I use my limiting reagent in my stoichiometry to determine my theoretical yield. Right, mole ratio. HCl is to CO2. 2 is to 1. 0.02 is to